So we typically start at like 10:35 to let more people to join.
I think my camera is down. I don't know why.
I think your camera is working normally.
Oh, really?
Yeah, I can see you are moving.
Oh, I can't see myself.
Okay. Yeah, so actually, we in the QCE we see the VACSEN tutorial, and it's a very cool tool.
Yeah,
So we
yeah.
were there to see the presentation. Yeah, I think Professor Guan, you are not in the QC, you are not attending QCE this year, right?
Yeah,
So-
I registered, but at the last minute, I have some family issues, so I canceled the trip.
Okay,
So
I
yeah,
see.
yeah,
Mhm.
I was supposed to be there.
Okay.
We got several papers there, and
Mhm.
yeah.
Right. Yeah. So typically we will record this lecture and then post on the YouTube. So if you are okay with that.
Yeah.
Okay, cool. Thank you.
Okay.
对，我们又这个又把这个。
So I think it's the time to start, and I'll firstly introduce the simple bio of today's speaker. Dr. Qiang Guan is an assistant professor in the Department of Computer Science at Penn State University. Dr. Guan is the director of Green Ubiquitous Autonomous Networking System Lab, so Guan's Lab. He is also a member of Brain Health Research Institute at Penn State University. He was a computer scientist at Los Alamos National Lab before joining KSU. His current research interests include fault-tolerance design for HPC applications, HPC cloud hybrid systems, quantum computing systems, and applications. So let's welcome Dr. Guan, Professor Guan, to give today's talk.
Thank you, Jiding, for the introduction. Okay, so it's my great honor to share some recent work in our community, and I hope that through this my presentation, we can motivate more students and researchers from the classic computing domain and move into the quantum computing system domain. Okay, so today I'm going to talk about the title is Enabling the Robust Quantum Computer System by Understanding Calibration Data. Okay, so I compile multiple recent work in this presentation. So this is my very simple bio. Okay, I've been working in the industry, working in the research lab, and for different subdomains. So this is my lab. So my lab was generally sponsored by NSF, NIH, and the DOE. So we have several research track for AI, for system, for quantum computing, and the virtual reality. Okay. So today I'm just going to be focusing on the quantum computing domain in my current research lab. Okay. So first of all, I want to talk about my connection to the quantum computing. Okay. At the very beginning, I think everybody was, the first time probably got connected to quantum was this Schrodinger's cat, right? So that was the one example that I used in my quantum computing class for the first class, right? I think I remember that when I was doing the PhD, right? So we start to have this Big Bang theory, right? So actually, at the time, this guy's even though it's like a funny show, but typically they showcase some sort of lives of some scientists, right? So physics in the physics domain. Okay, but the first time I really got a chance to touch to quantum computing is through the when I was doing the computer scientists in the Los Alamos National Lab. So DOE has invested some hardware devices at the very early stage of the quantum computing. I think that's probably 2015, 2016. So we have this D-Wave machine exactly physically installed in one of the facility in DOE National Lab. So typically, I have been programming on this D-Wave 2000 previously. And to be honest, it's not really kind of a quantum computer. So it's more like a simulator of IC model that's running on certain kind of hardware, okay? So most of the widely accepted concept like entanglement was not well integrated in this hardware, okay? But until we have the IBM at the very early stage, our current, I think everybody using the IBM Quantum Cloud every day. But at the very beginning, its name is called IBMQ Quantum Experience. Okay, so their programming interface is really, really simple, very simple. And the resources, I think at the first phase 1, they only open 4 or 5 quantum computers. The biggest one probably is a 5 qubits machine. Okay, so at that time, I got the chance. I got some seed funding from the DOE National Lab, and I started to play with this quantum computer. But at the beginning, we cannot have too many things to be done on the quantum computer, quantum hardware, right? They're really simple. Okay, so next I want to talk about my research focus in the quantum computing. So we can, this can be considered as a general diagram, right? So when we have such kind of programmers, right? So we write the quantum applications, and then through the API services hosted by those hardware vendors, and then we can have our circuits, our codes running on the hardware, right? And then eventually the result is going to be returned back to the programmer, right? Which is a general programming, general kind of workflow. Okay, but actually there is a big gap, or a missing piece here, right? Most of the case, the programmers are focusing on implementing their algorithm and check out the results. But in most of the cases, they don't really understand how well their codes are running or executed in the quantum hardware, right? So I think that becomes a big gap, right? Sitting in between the programmer and the computer hardware, right? So in most of the case, the hardware vendors, I don't think they provide a good support, right, for the programmers to have a better understanding about these hardware pieces, right? So, for example, even though you can check out the dashboard to figure out the calibration data, under some sorts of general specs like quantum volume, number of qubits, such kind of thing, right? But still, it leaves the user as a really kind of jungle, right? I think this policy can be considered as you do whatever you want, but you take the risk, right? So in such kind of situation, I think there are a bunch of research challenges that we're currently facing, especially how we can help our programmers, right, to have a better chance to utilize the hardware, quantum computing hardware, right? So based on this, we're working on the hardware side. We do the hardware noise characterization. We try to evaluate the performance so that we can propose or we can recommend, right? So the best and the most reliable quantum computer hardware, so that they can select to use, right? So because when you open the dashboard of IBM, so they have so many machines, even for the same size of the machine, 27 qubits machine, you got so many choices, right? So apparently, right, so they are not running exactly at the same kind of conditions, right? So we need such kind of understanding so that the programmers or the users may have a better understanding and make the best choice for them. Okay, so based on that, we're building a bunch of visualization tools so that the developers doesn't have to dive into the details of those metrics representing the performance. So they just need to simply say, hey, this machine, it's the status is green, use it, right? Another one is yellow, right? You may consider for the second choice, something like that, right? So make this as simple as possible for the programmers, because I think most of our programmers may from different kind of backgrounds, right? Physics, chemistry. So such kind of tools, it will be very important. Also, we may need this to have a better understanding about the application, right? And also how our applications can survive in a noisy environment. We need some sort of parameters or metrics to even get for evaluating this performance, the potential performance of the application in the noise device. Okay, so yeah, here a bunch of background saying, right? So we have multiple vendors, and they all provide different kinds of services, right? So based on their community support to the community. Then let's come to the motivation part. Actually, as we all know, that the current quantum computers are regarded as the NISQ devices, right? So that means they're intermediate scale and they're noisy. Okay, so this gives you a simple example, see like how this noise can play in this application, right? So for this BV simple application, you can see that very simple circuits, but actually when we run it on the real machine, the result is slightly different from running in the ideal environment. Okay, so that's just because we have such kind of thing called quantum errors or quantum noise. Sometimes they use the interchangeably. Okay, so typically for the quantum errors, people are trying to build this kind of performance metrics like what we have been doing in our classic computing. We have this like cache miss, cache hit, right? So such kind of performance metrics is representing the hardware performance. Similar thing, most of the vendors releasing their performance metrics related to the quantum errors, right? So most of the famous one, I think everybody probably have ever studied that, T1, T2. They're really kind of the physics hardware status related metrics. Okay, but there's another group really come from the operations, right? So we call them quantum operation errors. Typically, this is from the gate errors and measurement errors, right? So when we are applying such kind of gates, right? So definitely some errors may be already added into the circuit and into the computation. And we call them, in this operation errors, right? So typically, different hardware vendors will release more or less a similar kind of spreadsheet of their performance metrics regarding the quantum error and the noise. Okay, so we know that it's important that we have to survive, right? So multiple researchers, research work have tried to solve this problem. Dated back to 2019, right? So, so that built up the kind of literature background. So our work, one of the work that we are focusing on is we want to analyze them and try to see if we can predict the quantum noise, right? If we can predict the quantum noise. So there are some benefits, right? So if we can predict them, so definitely, the users, right? So we are my research work, you can see that always standing at the point that we serve for the users, right? Serve for the users. So if we can make a good prediction about the errors, right? So definitely users can save some time, right? So they don't really want to sitting in the queue and waiting for like 1 or 2 days and get their circuits running, but just the hardware just return a bunch of junk. Okay, and also they may save some money from using these commercial services from AWS brackets, for example. Okay, and like we can further reduce the uncertainty of the results. Okay, so such kind of a prediction can help the user to make the best choice to decide when and where I can run my codes, right? So for the masters, we're typically looking into the temporal analysis. So we want to see if we can explore such kind of temporal model for the prediction. Okay, so and also based on the such kind of prediction, definitely should be categorized based on the multiple categories that we're using in the quantum machines, right? So, for example, like noise state, quantum capacity, topology, and also the cost. So that build up, the overall kind of cost functions for the user. Okay, but we probably just play a part of them. So this is about the data collection. So even though I guess currently you can just probably pull all the calibration data from IBM, but we started from 2019 and manually save this data, right? Previously, because they don't really have the database and the QuCS is not well maintained and connected to their backend. Okay, so the first work we try to summarize, these the characteristics of the hardwares. So we look into the topology of the qubits, and then we name them different topology: linear, ring, tree, mesh, double ring, and octuple ring. Okay, and also we track the processor models and their quantum volumes. Okay, so we did some characteristics, and we also study the calibration and the internal function about their pulse generation method on the single qubit machine. So it's working well. Further validates the next step research. And from this one, we can see that right. So definitely different quantum computers, right? This is based on the different calibration. Calibration, the dates of the calibration, okay, data were collected. So we definitely can see that the different machines are performing differently, and the different qubits are performing differently. And when we see this kind of waves, that motivated us to think about if there exists some kind of temporal model so that we can try to figure it out. Okay, so besides that, we also did some study on different processor type, and also try to compare, right? So at a different stage of this computer, for example, like this one is showing the one of this machine in 2019 and 2020, right? So it seems like we are improving our management and hardware performance tuning on the backend, because previously the performance is really unstable, and the noise for this C0 errors, it's like 0.0023, right, at this scale. But in 2020, everything got greatly improved, right? So it's 0.00069. And also, you didn't see a lot of big peaks or trough, right? So it's relatively stable. So back to the previous question. So when we see such kind of a wave, right, we were thinking of if there exists any seasonal pattern, okay, seasonal pattern. For proving that, we simply apply the KPSS test, because this is a stationary test that can test that if this time series, okay, if this time series exists, the seasonal pattern. Okay, so from this KPSS test, and we're tracking different calibration data, T1, T2, C0, and the readout arrows. As we see that most of the p-values are larger than 0.05, which indicates that this time series of T1, time series of T2, readout and C0, they are stational time series, okay, which means that they have this time seasonal pattern. And based on that, we did the temporal analysis to make the prediction, right? So we apply ARIMA model, exponential smoothing models. And this, you can see that this is one of the examples that we put in one of our publications. See that it's quite predictable, okay, quite predictable. You can see that the actual readout errors and the predicted errors are very close, okay. So the next work is we want to, after we figure out, there exists a temporal pattern, and we also got really confused about when we are trying to choose the machine, how can we make the best choice, right? So we know which day could be the best, right? But another question is how these comparisons can be conducted between the machines with the similar configurations, right? So this is a work we published in Quantum Week, just I think last week, right? Last week, and this is we consider the time series of the calibration data, and we apply the a method called the degradation detection. The idea is simply we stretching the one of the attributes from the calibration data, for example, T1 of Q0, and then we apply this anomaly detections or degradation detections, and we figure out that if there is a big peak, right, so it could be considered as anomaly. And in our case, we call it performance degradation. And if this kind of degradation event was detected and observed, and we mark it as a 1, right? Eventually, we can build up a fidelity degradation matrix, okay? So in this matrix, for one of the domain, we indicate this the sample time, and another direction, that's the index of the attribute, okay, index of the attribute on that single machine. So each machine will have a fidelity degradation matrix so that we can just compare them within the same time of period, okay? And based on that matrix, we propose a multiple evaluation matrix, right? So here we are referencing some concepts from the classic domain. For example, mean time between such kind of events, right? So which means that when we see some performance degradation, right, in this time scale, at the time scale, right, how long we can expect the next one may happen, right? So definitely, the longer mean time between fidelity degradation, the better for that machine, right, for user to choose. And then we also study the distribution and study the correlation. We also focus on the qubits, right? So we try to figure out within the same machine for all the available qubits, either it's 7 qubits, 27 qubits, 16 qubits. So which of the qubits may have a more performance degradation events than the others? Probably that qubit is more vulnerable, or there's performance is less than the rest of the qubits. Okay, so I probably just skip this findings, and you can simply check it out from our paper. Okay, so next one I want to talk about the probably as Jidin introduced, right? So the recent work that we are accepted in TVCG, and we're going to presenting this one in IEEE visualization conference next month. Okay, so this is called VACSEN. So from the previous study, we found that definitely the community needs some sort of a tool, right, to be easy to be so that user can easily understand the quality of the machine, the quality of the qubits, the quality of their connections, okay, so that they can adjust their decision to make the best choice, right, best choice. So this motivated us to build this visualization tool. We can see that one of the motivations we have here is previously we did some tests, right? So we choose different qubits and for running such kind of circuits, and definitely, you know, the result is very different, right? So that we know that we probably should for user, right? For user, they may need to know, okay, if I just need 2 qubits, right? Which 2 qubits I probably want to choose, or which machine I probably want to choose. Another one is from one of the functions from the QuCS compiler, right? So because our physical qubits are not fully connected, so at the backend, the QuCS will do this transpilation to transpile the logic circuit into the physical circuit. Okay. However, all this transpilation phase, this transpilation operation actually is done by the on the hardware on the hardware side, right? So it's not transparent to the user. Okay. Typically, a user doesn't know anything about that. So we want to open that black box, so that we did some manual transpilations, and then we just want to compare them to see, like, okay, the result is very different, right? That means definitely there's different transpilation, even though you can find this equivalent circuit, but that the equivalent circuit may performing really differently, right? Regarding the noise or fidelity. Okay, so this is the general framework of a VACSEN system. So we have the data interface that keep pulling the data, calibration data from IBM backend. And we have some internal data processing, okay, internal data processing. And then we have this visualization interface, visualization interface. So this is not only a dashboard kind of thing. Actually, we also added some functions for user to make the selection of the machine. And also you can make the selection of the transpilation. And after you make all these decisions of your codes, you can just simply, right, submit through our interface, right? You don't really need to go through this IBM Quantum Cloud to submit your codes, right? So because IBM Quantum Cloud didn't give you this kind of comparisons between the performance of the hardware pieces, right? So but we do, right? So through this interface, you know which machine is performing better than the other, or historically who is better than the others. And then you can upload your code and submit based on the current selections through our interface. Very simple, okay? So, the major comparisons we did is with IBMQ, right? So most of our user interview we have done is to compare our interface using our interface and IBMQ interface. This is a typical interface that IBMQ gave you, right? So, but you can simply see that they just show some data, and they never gave you any instructions. Say like, okay, what's the best choice you can do, right? So I think it's reasonable, right? So they gave this freedom to the user, right? And they don't really want to direct the users to, you know, to one machine and make one of the machine super busy, okay? So this is the major interface that we're trying to compare with what you can get from IBMQ, right? So here we simply partition this user interface into 3 different areas, right? So on the very right side, we see all these control panels, right? For the control panels, and you can select this time range, how long you want to check his history, and what's the time interval, every day or every week, or every Friday, if you want to run your codes on Friday, every Friday, right? So check the performance every Friday. So, and then you can select which major calibration data you want to check, right? So T1, T2, or readout, or you may just switch between this different calibration data. And when you switch this one, and you can choose this for this demo's purpose, we pre-upload some algorithms. Okay, so pre-upload some algorithm, and then by selecting. But actually, we are currently building the system that's which can allow the user to upload their own codes, right? And after that, you can compile. Click the compile button, and then they will showcase all this first layer interface. Okay, first layer interface. So on the very on the left side, you can see that we pump out all this quantum backends, right? So your account can access typically. So because you are selecting different button, and then you can see that associated with this different calibration data, you can see this dot. Okay, this dots. This dots are representing the currently in this case is readout errors, right? Readout errors, and we use the color and the shape of the dots to indicating good or bad, right? Good or bad, very simple, right? So I think most of our users want to simple thing. I want the same thing. You actually, if you can do everything for me, that will be the best choice, right? So based on that, we will see like to compare. If you want to compare, we can compare multiple performance of this from the different servers, right? And also we have this bar indicating how many jobs are waiting in the queue, okay, at the current moment. So then, because this is only like a single qubit associated calibration data, right? We also need to know the CNOTs, because CNOTs is also one of very important metrics, CNOT errors. So that will be a little bit challenging because the CNOTs definitely involving the topology, involving the connectivity, right? So the novel part I think we have done here is we designed the visualization of the CNOT error rate in this way, horizontally, right? So now you can see that if these bars, right, these bars connecting two qubits representing the CNOT error rates on that connection, and if it's approaching to the right side, that means the CNOT error rate is high, right? If it's close to the left side, the error rate is low, okay? But how we can justify that, Legos is better than PERS or something, right? It still, needs a little bit kind of better visualization, right? So based on that, we develop using the this density matrix, right? So this so that you can see that we can see if more bars on the right side, right? So definitely, the density on the approaching to the right, right, will become bigger, right? And then we use the color, still using color and the shape. You can simply select, what's the best choice. For example, on this day, February 12th, right? So definitely, if you want to choose between Jakarta, PERS, and Legos, right? Definitely, PERS is not going to be what you want to run, right? So the choice, right? Typically from this CNOT error rates perspective. But at the same day, Jakarta is not performing well for the readout errors, right? So there are several red dots here. So maybe for the best choice that the user can make is go for Legos, right? And then you can see that, apparently Lego is a little bit busier, right? A little bit busier. And the PERS is also busier, right? So I think its performance is good. That could be another reason, okay? So the second one we want to show is for demos, for displaying the translation, right? Displaying the translation performance. So for doing that, in our case, we just randomly using the QuickSkit to randomly generate hundreds of the transpiled circuits, right? And we use this visualization to indicate, right, so the current score, okay, the current score of this circuits, transpiled circuits running on the specific hardware pieces. In this case, it's Jakarta, right? So we choose Jakarta and then run the transpile, and then this gives us this analysis. So the key idea for this analysis is we will profile the number of the qubit, single qubit gates, and the number of the CNOT gates used in this circuit, so that we can have a better understanding about the usage of the qubits, right? For example, if one of the qubit is really running in, has a higher readout errors, right? So simple idea is we don't really want heavily using that qubits, right? If one of the connections are experiencing much higher CNOT error rates, so definitely you don't really want to have really high portion of the CNOT gates sitting on that direction, on that connection, right? So that's the basic idea. So that based on that, you can simply see that for different transpolations, and you can see that we gave this visualization, and we summarize the overall score. Okay, overall score. And you can check out the details from our paper. Okay, but simply you can find out we give the score, which means that if we use this transpilation on this selected hardware, right? So the possibility of getting much accurate results will be higher. Okay, will be higher. So that's this kind of an indication, so that you can simply check out right which is could be the best transpolations. So I understand that IBM gave us some by default they will do some compiler optimizations, but I think this, even though this tool can still has this value, so that it can definitely reevaluate, okay, as a third part kind of checker, okay, third part of a checker. So. And then based on what you selected the machine, selected the transpiled circuits, and you can directly run it by submitting the job, okay, to the hardware backends, okay? And then the result will be returned to you through this interface, okay? So that's the basic idea. That's the basic idea. So yeah, this is some design approaches. So I already just covered. Okay. The last one I want to talk about is on the other side, application side, right? So in most of the case, when we write our circuits, we don't really understand how good our circuit will be, right? So definitely there will be different type of implementation for the same algorithm, right? But we don't really know that, on this applications perspective, right? So how robust it is. So based on that, we propose this quantum vulnerability factor. We call it QVF. So this work is published in DSN this year. Okay, DSN this year. So typically we're using the Michelson contrast, and we do this. We do the error injection, okay, error injection into the different part of the circuits, and by summarizing their final output, so that we build up this QVF result, okay, QVF result in this way, okay. So we inject faults into the different we inject the errors, different errors into the gates, and typically they give us this different QVF. So if you want to, you can check out the details through our DSN paper. Okay, DSN paper. So I can maybe probably, since okay, we still got time, I may probably just open that question a little bit to show here. So the QVF is scaled from 0 to 1, okay, scale from 0 to 1. So by injecting the errors with different kind of angles of shifting, theta and phi, right? So, and then we want to check out this, compare this compute this contrast, right? So based on this, the probability of noise-free run and this noisy run, okay? And then we got this QVF. So by injecting faults, different types of fault into the gate, and we can see that, this will be different, right? This will be different. So if we compare different applications, you can see that for this area, right? This area is really low. This area is really low, but this area is not that bad comparing to these two, right? Comparing these two, right? So which means that the QVF is higher. That means it's more vulnerable. So definitely this application QFT may be really vulnerable if the error rates. So the errors, okay, is performing in this way or in this way, okay, in this way. So based on that, we did have some observe some patterns, right? So the first one, the fault propagation is definitely depend on the algorithm, right? So different algorithm may have a different kind of robustness, right? Robustness. So this robustness is not only regarding to their initial features or characteristics against the noise, but also this regular noise, but also it's going to be able to be used to address how vulnerable this application can play against this radiation effects, the errors from the radiation effects, which is another potential source of the errors. Okay, the errors. So we also see some other things from the error injections, right? Definitely, if we inject faults into the different qubits, we have different impact, right, for these applications, right? So this may motivated us to think about the mapping strategies could be different, right? Mapping strategy could be different. Also, we do this QVF distribution to check out the scaling. Definitely, this scaling may be different when we have for the same applications, right? So from small scale to the bigger scale, right? So this QVF, some of the application is showing different performance, and some of them is not, right? For example, like a BV algorithm, right? DG algorithm, but for QVF, it's really showing a very special curve, right? Very special curve. Okay. So this is the overall publications we have already achieved for the past 2 years. So if you are interested, you can definitely check it out. So this is our current collaborations. So we collaborate with National Lab, we collaborate with multiple universities, and we collaborate with the clinics, right? So clinics, since we are sitting in Cleveland area, so we have a close collaboration with Cleveland clinics. And it's very interesting that Cleveland clinics recently purchased the 2 quantum computers, and they will be, let's call 2 quantum computers from IBMQ, and these 2 machines will be physically installed in the hospital's data center, which is the first time probably in the US that IBM has a quantum computer installed or running or operated out of their facility. Okay, and we are a part of this collaborations and through this Cleveland clinics. Okay, so the last thing I want to talk is the future of quantum computing system. Okay, since this talk series about quantum computing system, and I always mark myself as a system guy, right? I originate from the distributed system community. I do cloud, I do HPC, and I do this quantum computing system. I think in this area, right? So we need a lot of efforts, right? Everything is every direction is empty. For example, like and also exists a lot of opportunity. For example, we need in classical computing we have the compiler, right? So and in quantum computing we also have the needs for quantum compiler, right? Classical computing we have the runtime system, right, to manage different type of resources and a multi-core system. And in quantum computing, we also need such kind of runtime system, right? Runtime system. Then how about the failure management, right? So HPC in classic computing, we do ECC, error correction. We do chip kill. And in quantum computing, we also do the quantum error correction. You can see that there are a lot of overlapping and the potentials, right? So, but I don't believe that currently we have a big enough community to conduct all these tasks from different areas, right? So we can see that the quantum computing was initialized by the physics guys, right? So they build up the system, the hardware, but eventually, right, they will need to connect the hardware to the user, right? Hardware to the user. And we have been working on the classical computing system for many years, and we know how to serve upper level applications, even though maybe not all the current applications can take the benefits from the quantum computing, but we do have a small portion of them, and they need to be connected to the hardware, right? Hardware, and that's our opportunity, and that's I think what we should do to make it happen, right? Make it happen. So it's kind of the physics guys build up the machine, and now the mission was passed to us, right? To build up the system. Maybe we have a quantum operating system, right? Quantum runtime system, right? Or some like the performance libraries, monitoring tools, right? So that the upper level application developers may use the hardware, right? So very easily, right? So that concludes my talk. And here you can visit the vaccine.github.io to experience our online demo. Okay, I think you can through this QR code as well get to connect you to the demo. Okay, that's all for my talk. Thank you.
Okay, thank you so much, Professor Guan, for the very insightful talk. So let's open the floor for the questions. You can either tap in chat or unmute yourself to ask questions. Well, when you think about questions, I actually have a question. So we actually also work on something like the prediction of the quantum noise. So I think I'm very interested in the QC paper, the prediction of the degradation. So I'm wondering, what do you think of a good granularity of the time? So for example, are we able to predict several days later or just several hours? So what do you think of the proper time scale for the prediction?
Yeah, I think that's a good question, Henry. So typically, our research in this area is really constrained by the vendors, right? By the vendors. So you can see that definitely every minute or every hours, this arrow related performance may change, right? But it's really hard to keep tracking or pulling the data in a very high frequency, right? High frequency is like doing the calibration very frequently, right? We can see that IBM have already changed and increase the frequency and reduce the interval of calibration, right? So, yes. But I think currently what we can do is still based on this the observed or the released calibration data from the IBMQ. You can see that it's really hard to say like, okay, based on this calibration data, we can have a really, for example, like if they gave us every 24 hours, and we can see that, okay, how about in the middle, right? So I think it's a little bit challenging to tell, right? So what's going to be in between this 24 hours? And it's really hard to validate your method, right? You can make any kind of guess or prediction, right? And it's hard to validate it. It's hard to validate it. Most of the case, I think this is a little bit limited to the operations and the management, right? Operations and management.
I see. And also many of the noise are just random, so there is no significant pattern, right?
Yes, yeah. But that's why I think we build up this framework, we build up these tools, right? So hopefully in the future, when we have like a better understanding of the errors, right? So this kind of tool may be adjusted and customized still can be helpful to the user, right?
Yes, right. Yeah, so maybe we can discuss offline because I'm very interested in doing this machine learning based. So now we are trying to train some deep learning model to do the prediction of either the future noise or the fidelity of the circuit. So also very similar to the third work you introduced, the vulnerability prediction, right? So
yeah,
I think that is for like if you change some parameters or inject some noise in the rotation angles, what would be the final impact of that noise, right? So
yeah, yes, exactly, yeah. So I think the user needed to have the understanding about the two parts, right? So when they write the code or they design their circuits, they need to know, right? So how good their design is, right? Literally against this general errors may happen, right? Even though the noise or the errors may be performing differently on different machines, but in general they need to have an idea, right? It's just like just something like when we write a code, right? Classic code, and we may want to profile it, right? We profile the performance, right? Sometimes we do static profile, right? Static profile, which is reasonable, right? This kind of thing, the QVF, is a similar kind of static profile, right? And now at the current stage, when we talk about the performance, in my opinion, when we talk about the performance of the quantum computing system, performance is only tied to the noise and errors, right? Because it's like it's not reasonable now to compare how fast it could be, right? Compared to classic computing, but we can compare how robust or how reliable their service or their hardware is, right?
Right. Yeah, and exactly.
That's the major. I think that's the major flag for comparing the performance of quantum computers.
Yes, I'm wondering if your group is looking at some of the deep learning based. So recently we have ICCAD 2022 paper, which is exactly the same idea. I just sent in the chat. So basically we collect the data for many of the random circuits, and then we do the reverse of each circuit. So in that case, we can just do one measurement to get the probability of success trial, because we know the correct one should just be the of 0, 1, because you just apply the circuit and then the reverse or inverse of the circuit. And then our idea is train a transformer model based on like tens of thousands of experiment data. And then we can do the prediction according to the T1, T2, and also the graph structure of the circuit, the operation graph. And then we can say, oh, this circuit running on this machine will get a probably 0.5 success rate, or something like that. So
I think that's a good idea. That's a good point. Yeah, that's a good point. Yeah, we need such kind of profiling tool or performance predicting tool, right? So in the community. So especially when our user, right, are very familiar with the classic computing environment, they have so many tools right there, right?
Yes,
you can do this
right.
profiling. You can even do this predicting, right? So see like, okay, what about I run this machine on, one of the supercomputing in Oak Ridge comparing to on another supercomputer in Argonne, right? So they're architecture different, but through this support of the tool, they know, okay, yeah, definitely, so there will be some different performance and,
Right.
have some general idea. But in the computing domain, we don't have such kind of thing provided to users. So this is making the forcing the user to leave or refuse to try, right? Refuse to try this machine. So I think that's our mission, to build the tools for quantum computer systems, so that we can have the chance to invite more users. For example, like I through this my current collaboration with Cleveland Clinics. So they do some like drug discovery. They involve the quantum chemistry stuff, and they do the medical image processing, right? So definitely, some quantum machine learning algorithm may help them, right?
Yes.
But they don't really understand how things running and how their performance can be predicted, right? If this is unpredictable, why they want to try that, right? I think that's the current barrier, right? This is the current barrier. So we need to connect to the user. It's like that's the mission of our system guys, right? So we build the system to make the user feel comfortable to use the hardware pieces.
Yes, actually, I like a lot of your idea of like from different vendors or different cloud. Actually, for the classical different computing, I talked to Ian Stoka at Berkeley, and they are building a system which is exactly like for Amazon AWS or Azure, the same computing resource, but from different clouds, and they are trying to build a intermediate layer to help you decide which one you should use at this time. So that's
that's a really tricky part, Henry. So that's a really tricky part because so if we have any like audience from the vendors, then they will be really kind of pissed off, right? So they don't like that. To be honest, they don't like that. Because you're gonna be poking, this is this is a big point, right? So, but for the user, I mean, they need this kind of information cross platforms, right? So I think we should push such kind of effort to release the performance that can be compared between the vendors, so that some vendors know that, okay, these guys cannot be fooled, right? So they know they know everything. So they probably may have to push to improve something. Right. Currently, everybody is isolated. You cannot compare them, right? So even though, say like IBM say, hey, I do this quantum volume, and then the Honeywell say like, okay, you do quantum volume. I also follow this quantum volume, right? So they need to adjust all as well to come to something like a more general evaluation metrics. But quantum volume is really kind of static marker kind of thing, right? It's like it's just like you purchase CPU, like it's 1.8 gigahertz, right? But you can tune the frequency higher or lower, right?
Right. Yeah, that's true.
Right.
Yeah.
Okay.
Hey, Qiang.
Hey, Charles.
Just have a quick question.
Yep.
It seems like there are so many variants from different vendors, so it is a big burden for the system programmers. So typically, what do you think is a good obstruction to hide these variants at what level?
So I think currently, even for the calibration data, so different vendors have their own different formats, right? So even though it's like a major, most important in T1, T2, they all the same thing, but this for the operation errors, so they're not the same. I think we needed to through this some research doing some research through the research efforts to try to mine, which feature, right, are most representative, right, most important to the user or to the performance, tied to the performance of the application, so that this variance between the vendors probably can be, sort of solved, right? So and this way, so some of performance metrics you release are probably not making any sense, right? So, or it's not very helpful, right? So why you want to show that, right? So the vendor also needs to know that, we know it, right? We know it, don't fool us. Yeah.
Yeah, another thing, like in terms of quantum errors, how you get the ground truth?
For the ground truth, you can run it in a simulator, right? I think it's similar to what we have been doing in our classic computing for this right, software error stuff, right? So even though software error is really rare, but this error is really
yeah, but I mean, like in production system, like it seems like there is no mechanism for us to avoid this. Like we need to detect it something. But at least
you mean detection?
Yes.
I think it's impossible. This the state of the qubits are operated by the gates. So literally, we don't know, what the gate may guide the state change it to a new state. Right? Even though we have some knowledge, right? So some knowledge should be there, but we cannot keep tracking that, right? Keep tracking that, and there may also exist some sort of error propagation, right? Some small errors that was brought in within certain kind of gate, and the error may sit there, and next time when the state was changed again, right? So that may further got amplified, right? The impact got amplified. So yeah, I think we still have a lot of things we don't really understand.
Yeah, I have one point to add.
For current systems, there is no mechanism for us to know whether this computation is like trustable or it has some.
There are several. I think there are several works on do the debugging, from the Yipeng Huang and Margaret Matonesi group, and also I think in general for the detection of the error, we can use the quantum error correction. It's basically you implement the one logical qubits with many physical ones, and then if one of them is encountering some error, the parity between the qubits will be changed. So you have some syndrome qubits to do the measurement. So you can know, oh, this qubit is undertaking an X error, and then you can apply an additional X gate to do the correction. So that's I think in the quantum error correction domain, we do have some tools to detect errors.
Okay.
They're expensive. They're expensive. So at the current stage, I think it's not
it's more like hardware, like a parity code. Or
right. Yeah. Yeah, and you see that it's expensive, right? So ECC and the chip Q, you have like 10% or 30% of the resources are used for this kind of checking or correction function, right? So. And then this kind of overhead is not affordable in our quantum computing system. So that's why, So I have ever organized a student competition. So in 2019 about this quantum error correction. This to me is algorithm level. At the algorithm level, it's very reasonable and reliable. The big challenge is just for how they can be integrated into the hardware, right? So it's like too expensive, and it has a really high requirement on the connections, right? Connections. They have to the oscillator qubits have to be really close to the qubits that's under his monitoring or checking or correction. So the conditions are some sort of hard to satisfy.
I know question, simple question is like, based on your talk, it seems like right now if we're programming a quantum machine, it seems like just like writing the quantum circuit, and more like we program the FPGA. Is it similar? Like?
Yeah, I mean, yeah, most of the case, right? So you need a little bit kind of support, like visualization, right? I know that some of the developers may need the Bloch sphere to help them to try to imagine the gates may how the gates may change the state of the qubit.
Mm-hmm.
So yeah, that's something that's there's another work we collaborate with this also from the same team we built for the vaccine. So it's called the Venus. So we submit to CHI. So we try to build some another easy to understand the visualization for the debugging, right? So when you do this, you add something, you add some gates, and then give you some easier to understand what's going to be the consequence for the final result or something like that, right? So typically, I think programming on quantum computer is still a little bit challenging. So yeah, but
it's challenging because of like no tools for writing the circuit. The circuit.
I think that the concept is different, right? The concept is different. I mean, so literally, you're not like doing some like general operations like addition, multiplications, right? Shifting, right? This kind of thing. So what they're doing is like just playing with the state of the qubit, and you have to imagine that by doing such kind of operation, adding a X gate, a H gate, and the result gonna be turned some way, right? So you may have to have some like experience, so that the consequence could be predicted or could be understand when you add some operations there, right?
Mm-hmm. I think maybe, I mean, I don't know, just like feel like at this time it is more like when we build a computer from like
yeah,
8. There is many like some high level instructions about like maybe we can see saw some like information about like multiplication.
Yeah. You see, if you check the roadmap of IBMQ, right? So this it's going to be coming. There's a multi-core and the communications between the cores, right? Even the communication between multiple chips, right? So it's going to be coming. Typically this is why I say like typically this is just going to be copy pasting everything happened for the past 20 years again.
That makes sense.
Yeah, people just use their knowledge, so how they build it. But this is like from architecture perspective, right? Architecture perspective, right? It's like but it's still right. So when the hardware or architecture build up this multi-core or kind of architecture, right? So then we at the operating system level, right? So we needed to adjust to this, right? We still need like some middleware to support them, right?
Mm-hmm. I see. Yeah, good talk.
Yeah, we can talk about that offline.
Yeah.
Cool. Yeah, I think we definitely have a lot of research overlap, so maybe we can also discuss offline.
Yeah, sure.
So,
Of
okay,
course.
cool. Yeah. So, any other questions from the audience? Okay, cool. If not, I think it's a little bit over time, but let's thank Professor Guan again for the great lecture, and thank you so much for this very understandable introduction of this whole tool chain. So I think that's about this week's lecture, and I hope to see you guys next week.
Thank you. Thank you for the organization. Yeah, thanks.
Thank you so much.
Thank you for the great talk. Thank you.
Yeah, bye.
Yeah, see you next week. Bye.
Bye.